what differential equation problems are going to look like. These are all going to be more or less the same, and I'm using the same kind of example. So these are going to be problems that are based on the drag force or some kind of resistive force that is proportional to velocity. That's the big part, is that for this whole set of conversation, we're going to talk about forces that are proportional to velocity. They come in a variety of kind of subtypes, but in every single case, you're going to have a force that is negative because it's going to be in the opposite direction of the velocity, a constant in either v or v squared. I mean, it could be any actual power related to v, so it could be v to the 1/2 power or something like that, but it's going to be something usually of this persuasion. And there's really only a few subtypes of these questions that generally get asked, but they all have the same kind of look to them. For a basic, and like I said, we're using coffee filters, for a basic kind of drag problem, they're experiencing two forces, a downward force for gravity and an upward force that represents drag. But the drag force is some constant times the velocity. I'm losing a negative sign because I have arrows now. Is that okay with you guys? And of course the downward force is mg. So when you first drop it, v is 0. So because the velocity is 0 when you first release it, we know that there's no drag force, so the object accelerates. But the moment it accelerates, that means its velocity changes. And as the velocity increases, the drag force increases. Eventually, you will reach a steady state condition where the downward weight is equivalent to the upwards drag force. This steady state condition is known as the terminal velocity or the terminal speed. And clearly, the bigger the mass of the object, the higher that speed's going to be. It's in the numerator of this fraction. But that cross-sectional area part, and it's not just cross-sectional area, the shape has a lot to do with it, obviously plays a role too. So if you increase the cross-sectional area, you decrease the terminal velocity. Just think of what a parachute does. A skydiver who's falling is going to reach one terminal velocity, probably fatal if they hit the ground. So before they hit the ground, they increase their cross-sectional area dramatically by deploying their parachute. That changes the value for K. That reduces the terminal velocity, making their crash into the ground something that they can survive. Today's modern parachutes can do a great job spreading out nice and big to create a huge amount of drag force, thus reducing the terminal velocity to a very small amount. It's the in-between time that we want to study when it comes to dealing with differential equations. So far, all we're seeing here is algebra. But in a minute, we're going to talk about, can we come up with an expression for what the velocity does under these circumstances? That's the part that's harder. Now, I do want to talk to you about different styles of this question first, and then we're going to dive into one. So just to make sure we have some vocabulary, there's different kinds of drag. The type we're looking at right now, where the drag is linear, tends to be something called laminar drag. That's when the air is nice and smooth and it parts around your object smoothly and cleanly to make sure that our object kind of goes through the air gracefully. However, there is what's known as turbulent drag. That's usually when the drag force is bigger, more proportional to the velocity. And that is because the air doesn't part so cleanly. We get these little vortexes behind it that create a bit of a low pressure area behind the object that increases the amount of drag. And I'm sure you've heard the word turbulence before. That's when the air isn't smooth. So that's what the description is about. So turbulent drag, if you've ever had a big truck pass you on the highway, You've probably been buffeted around in your car. That's because that truck is parting the air in a turbulent way. It's making little waves in the air, and you're experiencing them. So this is the most basic kind of problem, is one of these where the object is merely dropped in the air. So this kind of problem is the V naught equals 0 style problem. It's pretty straightforward, but they'll camouflage it. They will put it in problems that don't look like this, and I've included one in your practice that I posted this morning. There is a problem that looks just like this, but a lot of students mistake it for something else. And it has to do with viscosity. Anybody know what the word viscosity means? A viscous liquid? No? You guys don't know the word? Viscosity is the easiest way to say the word or to understand what it is just thickness. How thick is something? That's not a great overall description, because there's other things that have to do with viscosity. These problems, what they'll do is they'll have like some viscous fluid filling a container. I don't know if I want to make it look like that. Let me see. Let's make it look like this. Some viscous fluid filling a container, and they'll drop like a marble in it. And they'll say, we're doing a viscosity test. And, they're dropping different sized marbles in there to see how long it takes to reach the bottom. Or you're going to test a bunch of different fluids to see which one is more viscous by dropping a marble in it and seeing how long it takes to reach the bottom. They'll give you a lot of extra language in there. This is just a drag force problem. Okay, we're going to drop the marble in there. It's going to start with a V naught of 0. It's going to experience a downward force due to gravity. And there's going to be an upward force due to it having to move through the fluid. And that's going to be an upward force. They won't call it drag, but I sure bet it's going to be something with maybe some fancy symbol in there. They'll say it has to do with the viscosity, and you'll see velocity right after it. So don't be fooled that this marble dropping through a fluid has anything else but the same kind of problem as dropping the coffee filter through the air. So they'll can't, like I said, they're going to camouflage the question sometimes. That's just them trying to distract you. All of these problems are the same if you have a force that is proportional to some version of velocity. They're all done the same way. You're going to do the same things. Everybody got it so far? Now, there are other ways for them to state this problem. One of the more common ways is to reduce the part that has to do with air. And they'll say something about there's a surface, and on that surface there is a box. And the box has an initial velocity of V naught, and it's being pushed towards some surface. And they'll usually have two parts of this problem. The first part, the surface will have just some standard kind of coefficient of friction. Coefficient of friction imparts a force on the object. That force is constant. So the Galilean motion equations come into play here because the box is going to experience an acceleration this way. That doesn't change. It stays the constant the whole time the box is going across that thing. And then there'll be part B of the problem. And in part B, they coat the surface with a new material. And that new material has a force that is proportional to the velocity. Again, it's a drag problem. It's just a drag force. The only difference in this version of the drag force than the others, there's no gravitational force here. And we've given the object a starting velocity. Clearly, this surface is going to bring the object to rest. All good? All right. We're going to do, believe it or not, this problem first. But there is another version I do want to throw at you, because this one would be the most complicated of all of them, should they ask it. I haven't seen it on the exam yet, but you know how I feel about that, right? Whenever there's a problem that we haven't seen on the exam, we need to make sure we take a little extra time to talk about why that might or might not be on the exam. And it's still a standard air resistance problem, with the only difference being that we're going to throw the object up into the air. And the reason this problem is different and begs looking at is because when you give the object an initial velocity upwards, one of the things you have to be aware of is on the trip up, it's actually experiencing two forces downwards. It's going to be experiencing the drag force downwards and gravity downwards. So on the trip up, it's being slowed by two forces. One of them is disappearing The drag force is getting smaller the whole time because the object's velocity is getting smaller the whole time. But it's going to reach the top, whatever its maximum height is, and when it reaches that moment, it's going to stop for an instant, drag force goes to 0, and then begin its trip downwards. Now, we've already had a moment to talk about that trip downwards, where gravity is pulling it downwards, but now the drag force changes direction and starts building upwards. One very common question to ask about this is, what takes longer, the trip up or the trip down? And if you've been studying this whole year, you're going to say, well, they're the same. Well, that's because this whole year we haven't really been talking about air resistance. The moment we add air resistance, it's not the same. The trip upwards is shorter than the trip downwards, because on a trip upwards, two forces are trying to stop it. On a trip downwards, one force is trying to prevent it from going downwards. So whenever you throw something in the air, it actually takes longer to come down than it does to go up, just because the forces change direction. So this is a harder question, but they often don't ask the mathematical part of this question. They ask the part of the question that I just asked. Which trip is longer, the trip up or the trip down? So let's do this problem first. We're going to talk about the dynamics of this question, what I'm going to expect of you, and how to earn all the points. First question almost always is going to be draw a free body diagram, that kind of stuff. And I'm not too worried about that. You guys tend to be pretty good. When it reaches that section, it's going to have three forces acting on it. There'll be gravity acting downwards. There'll be a normal force upwards, and we'll have a drag force backwards. The drag force starts big in this problem and gets smaller because the object is slowing down. So this will be where our drag force is. Now this problem is actually pretty easy to do because there's only the one force acting, that's the drag force. So that is the easiest of the differential equation problems we could be asked. But here's where you begin. They're going to ask you usually to create a differential equation that could be solved to find velocity as a function of time. I'm not going to write all those words down, but you should. So I'll say it a couple times because that's a clue. It's a key as to what you're being expected to do. So the question will be something like, write a differential equation that could be solved to find the velocity as a function of time. Write a differential equation that could be solved to find velocity as a function of time. Once they say that, your very first step is net force equals ma. That is your very first step. That's where they want you to begin every time. The next thing they want you to do is they want you to put the force in that's acting on the object. Be careful. The drag force is going to be opposing the direction of motion. Watch your negatives and your positives carefully here. This acceleration should intentionally be made negative, which means your force should intentionally be made negative. Make your velocity the positive direction every time. That will ensure you get your signs correct, because our force here is acting against the direction of motion. So our acceleration needs to be negative. You need it to work out that way. So this is one of those cases where I wouldn't just randomly pick a direction to call positive, because later in the problem, you're going to have to use V naught. Make it positive. It'll make your problem easier for you. Next, substitution. You need to substitute in the differential form of acceleration. Right there, you have earned the points that were for that question. So if it says set up a differential equation that could be used to find the velocity as a function of time, you've earned those points. They will often say set up but do not solve as one of the steps. And then usually the next problem is now solve it. Often they will even give you the answer, which means they don't care that you know how to do all of the steps. They care that you understand that there is a process to solve this differential equation. That's what they care about. So we're going to do the process to solve. So this is the first part. I expect you to be able to create the differential equation. You want to get a B on our next test? That's what you have to be able to do. And yes, there will be a test that's going to have differential equation questions on it. We'll have other stuff too. We're still having tests. I told you that. Now you want to create an integral from your differential equation. we use a process called splitting the derivative. And we've talked about this process before. I'm going to go through the steps. So that, although this is step one, is getting your differential equation, we are now going to split the derivative. That begins by isolating the derivative. You don't have to get it all the way by itself, but you might find it easier in most cases if you do. So isolate. Then the next thing is to do what the thing says to do, split the derivative. That means multiplying by what's on the bottom of your differential. So we're going to multiply both sides of the equation by dt. Next, you have to collect terms. Anything with, it's telling you what terms to collect. I'm trying to make this generic. But on this side, we have a dt, so anything with t has to be on that side. And on this side, we have a dv, so anything with v has to be on that side. So there is no t in this equation, but there is a v. So leave your constant there. But move that velocity over. This is collecting terms. Now, integrate both sides. That really means just putting an integral symbol on both sides. However, in physics, unlike calculus, we often do this as a closed integral, a definite integral, which means we set our limits, and you're almost always given points for choosing the correct limits. You guys are in calculus. I know that you guys do this as an indefinite integral, and then you solve for your constant later. In physics, you can do that too. That's fine. But they're going to give points for using your boundary conditions correctly. It's better to do it here. And it's simple. They will have told you in the problem already what the boundary conditions are, and I actually told you what they are. What we want is what the initial conditions of t and v are. And for us, the initial conditions were at time 0, the velocity was v naught. Now, if you had not chosen the direction of the velocity to be positive, you would have to make your velocity negative here. You'd have to remember that. And I think that's harder to do. That's why I always say make your velocity positive from the start. Now, the upper boundary is always going to be whatever your variable of integration is. The top part is always whatever this variable is. You just put it up there. Okay? If you can do